Because I mean, except for the zero vector field, because see, if the value of the vector field is non-zero at some point, you have a group of rotations around that point, right? So then if you use the definition of invariance, if you take a rotation, the value of the vector field at the point P will be the same as the value of, will be equal to both P and d phi of P, where phi is your isometry, but d phi of P is a different tangent vector. So then it's not well defined unless the value of the vector field is zero. Do you understand what I'm saying?
Yes, sir.
Because you have rotations around each point. This you have in R2, you have in H2, and you also have in S2. So in all of these, you can't get vector fields which are invariant under a full group of the full group of isometries. You can get vector fields which are invariant under subgroups. That is possible. Yes. So you can get vector fields which are invariant under, let's say, some one parameter subgroup of the group of isometries. That is possible.
Like in this case, rotation in R2.
Exactly. So for example, the radial vector field is invariant under the one parameter group of rotations. Or if I take a constant vector field, that's invariant under the two parameter group of translations in R2, right?
Yes, sir. Yes.
So you can get vector fields which are invariant under subgroups, but in general, if your isometry group is too large, if it acts transitively on unit tangent vectors, then it's impossible. The vector field has to be identically zero.
Okay.
Now there's a famous theorem of Noether, the same Noether as Noetherian rings, Emmy Noether. This is a theorem which is used in mathematical physics, which gives you that whenever you have a vector field, if it is invariant under a one parameter group of diffeomorphisms, then that corresponds to what's called a conserved quantity. The flow of that vector field, it preserves some quantity, some conserved quantity. So for example, the radial vector field is invariant under the flow of rotations. The radial vector field preserves the angle, right? It preserves the angle. So the angle is the conserved quantity. So this is a theorem of Noether, that these diffeomorphisms which leave the vector field invariant, those are symmetries of the vector field. Right? If you look at it in the picture, then the vector field, the picture of the vector field is symmetric with respect to those diffeomorphisms. It's invariant. That picture is invariant under those diffeomorphisms. And any such invariance, if you have a one parameter group of diffeomorphisms leaving your vector field invariant, that corresponds to a conserved quantity. So some quantity will be conserved. So for example, if I look at the rotational vector field, the vector field whose orbits are circles around the origin in R2, then that is invariant under the scalings. That is invariant under the scalings, and that corresponds to the conserved quantity, which is the distance from the origin. So the distance from the origin is the conserved quantity in that case. Does it make sense? Okay, so you can look it up. It's called Noether's theorem. You'll find it it's probably in Arnold's book of classical methods of mathematical physics. I think that's the name of the book, if I remember. I haven't seen it for a long time, but okay, so just look up Noether's theorem. That will tell you a bit more about symmetries of a vector field. Actually, this idea of looking at symmetries of a vector field, this is what led to Lie groups. Sophus Lie, after whom Lie groups are named, his inspiration was Galois theory. So, you know, for a polynomial equation, if you know its Galois group, that helps you to solve the equation, right? Yes?
Yes, sir. Yes.
So Lee's idea was, well, the Galois group for a polynomial equation is a finite group, right? Now, Lee's idea was, you look at a vector field, so that's a differential equation, right? A vector field gives you a differential equation, an ordinary differential equation. So just like polynomial equations, you can try to solve or at least reduce using the Galois group, the group of symmetries of the equation. The Galois group is the group of symmetries of the equation. So similarly, for the differential equation, you want to try and solve the differential equation using the group of symmetries of the differential equation. Now that group will be, in general, a Lie group. So instead of a finite group, you get a continuous group of symmetries. All right. And this can be achieved if you know enough symmetries of the differential equation, you can use it to solve the differential equation. All right. So I'll find a good reference for this. I've taught this many years ago, back in 2005. I taught this for some undergrads once, but I don't remember the details now. It's been 17 years, so been a long time. I'll try and find my notes. I'll send you. So I mean that's where Lie groups comes from. It's the motivation is Galois theory. The motivation is actually Galois theory. So instead of looking at symmetries of a polynomial equation, you're looking at symmetries of a differential equation. And instead of getting a finite group, you're getting a continuous topological group.
Yes, sir. My motivation for this question was also from the Lie group that we know, because if we are working on a Lie group, then all the left invariant vector fields are characterized by the Lie algebra. And also, if we look at, say, all left invariant differential operators, then we can look at the universal entropic algebra. So I was thinking that in case of the manifold, if we go to the isometry group, which is a Lie group, then maybe the Lie theoretic these sort of notions may correspond to something. That was my motivation.
Right, but I mean, here you don't need a Riemannian manifold. Lie's theory is quite general. You take any differential equation and you can form what's called the Galois group of the differential equation, which is a Lie group. And so there is a whole field called differential algebra, where you study what are called differential Galois groups. Okay, so I mean, this can be done purely algebraically. So it's called Lie-Vessiot theory or differential Galois theory. And there you look at, so I mean, the differential Galois group, it becomes, if you have a linear differential equation of order n over a field K, then the differential Galois group becomes a subgroup of GLN K. It becomes a closed subgroup of GLN K. So if K is R or C, then you get a Lie group. But K could be any field, actually. You can do, normally characteristic 0 you take. So you can do differential Galois theory over a field of characteristic 0. So if you're interested, there's a book of Singer, the same Singer as the Atiyah-Singer index theorem. There's a book of Singer about this differential Galois theory. I can send it to you if you're interested.
Sure, sure.
Yeah. So that is following Lie's original motivation for looking at the Lie bracket and symmetries of a vector field. So yeah. So you can look at symmetries of a differential equation. It's a purely algebraic theory. It's just over the complex numbers, it becomes related to complex analysis. And then it's quite interesting. Yeah. So.
Okay, sir. Thank you.
Yeah. Okay. So any other questions? Okay. So if not, then Bappa, you can start recording. If Orkujit, you can make Bappa the host for a second, then he can start recording.
So he's already recording.
Oh, it's already recording. Sorry, I didn't notice. Oh, I forgot. Okay. Okay, so let me start then. All right. So, last time we defined the notion of a Riemannian manifold, right? Where it was a pair M comma G, where M is a smooth manifold and G is an assignment to each point P and M. You assign an inner product G sub P on the tangent space TPM, and such that G sub P depends smoothly on P, in the sense that whenever X and Y are smooth vector fields on M, then the function G of XY is a smooth function on M, right? Where GXY is the function defined by P maps to GP of XP comma YP. Okay, so this should be a smooth function whenever X and Y are smooth vector fields. So this assignment G is called a Riemannian metric. Okay, so it's a smooth assignment of a tangent of inner product to each tangent space. And we already have one important example of Riemannian manifolds. So if M is a submanifold of Rn, then we saw that the tangent spaces of M can be identified with subspaces of the tangent spaces of Rn, which are in turn identified with Rn itself. So the tangent spaces of M are identified with subspaces of Rn. And then you can just restrict the usual Euclidean inner product on Rn. You can restrict it to each tangent space of M. So that gives you an assignment of an inner product to each tangent space of M. And this is easy to see. It depends smoothly on the point P and M, because if XY are smooth vector fields on M and P is a point in M, then the inner product between X and Y, this is the same, restricted to M, this is the same as the inner product between X bar and Y bar in a neighborhood of P in M, where you take U to be a neighborhood of P in Rn, and X bar, Y bar are smooth vector fields on U, which are smooth extensions of X and Y. Okay, so since X bar, Y bar are smooth on U, the inner product between X bar, Y bar is just the Euclidean inner product. It's summation Xi, Yi. So that is clearly a smooth function of Xi and Yi on the neighborhood U. So its restriction to M will be a smooth function on M in the neighborhood U intersect M. And so this function inner product XY is smooth locally. And so therefore smoothness is a local property. So globally it's a smooth function. Is this clear?
Yes.
Yeah, so therefore any submanifold of Rn becomes naturally a Riemannian manifold with what is called the induced Riemannian metric, because it's induced from the inner product on Rn. Okay, and then I finished last time by saying that, well, you know that any, so I mean, we have two notions of manifold, right? Either the manifold is a submanifold of Rn, that's a sort of concrete kind of manifold, or it is an abstract manifold with charts, right? Now, when it comes to looking at just manifolds without any extra structure, then these two are equivalent notions, and that is not too hard to show. There's a theorem which is not too difficult due to Whitney, the Whitney embedding theorem, which says that any manifold of dimension n, any abstract manifold, can be smoothly embedded into some R, into R to the 2n plus 1, actually, into R to the 2n plus 1. So, so any manifold can be realized as a submanifold of Rn. All right. But now the question arises, if I have a Riemannian manifold, so that means an abstract manifold together with a Riemannian metric, can I realize it as a submanifold of Rn with the induced metric, the induced Riemannian metric? And this is a much, much harder question. All right, because not only do you have to embed the manifold, you have to embed it in such a way that the inner product is preserved. So this becomes a deep question of analysis, and it is a rather amazing theorem of Nash called the C infinity isometric embedding theorem, that in fact, this is true. Any abstract Riemannian manifold can be realized as a submanifold of Rn with the induced Riemannian metric. Okay. So this is a hard theorem of analysis. This is really a theorem of analysis. And so, I mean, this is the theorem Nash should be remembered for, really, not the game theory theorem or anything. So yeah. Nash proved, in fact, two theorems. One is this theorem, the C infinity isometric embedding theorem. The other is called the C1 isometric embedding theorem. That is also amazing, but in a different way. So maybe I'll talk about that later after we've talked about curvature, because the difference between C1 and C2 will become apparent then. Right now, you may think there's no difference between C1, C2, and C infinity, but actually these are quite different. So at least C1 and C2 is very different. When it comes to Riemannian geometry, the difference between C1 and C2 is a big difference. So I'll talk about that later, I think. Okay. Any questions about this? Okay, so let me now start talking about what will be the main topic of most of this course, which are what are called geodesics. So these will be curves of shortest length in Riemannian manifolds. So let me just start by talking a little bit about Rn. Okay. So geodesics, or curves of shortest length, so let me first tell you about Rn, right, which you would know. So in Rn, remember, if I have a curve in Rn, say gamma, from an interval AB to Rn, then we know how to calculate the length of this curve, right, in Rn. What you do is you take the tangent vector gamma prime t at each point gamma t on the curve, and so you can define the length of a C1, or more generally piecewise C1, curve gamma from a closed interval AB to Rn to be L of gamma is the integral from A to B of the norm of gamma prime t dt. okay, where you take the usual Euclidean norm. Okay. And then what do we want to do? In Rn, a natural thing to try and do is to find the shortest length curve between 2 points, right? So what we all know what this is. This is the straight line joining these 2 points, this straight line. And so, if let's say gamma naught is a curve of shortest length joining x to y. So let's say gamma naught shortest curve from x to y. That means length of gamma naught is equal to the infimum of the length of gamma, where gamma is, let's say, let me just for simplicity take a C1 curve. Well, actually, let me take it to be a C2 curve to be a little bit careful. Gamma C2 curve from AB to Rn such that gamma A is x, gamma B is y. So we know this happens if and only if gamma naught is the straight line segment from x to y. And we know this we can write in a different way. So what is a straight line segment? It's a curve whose velocity is constant, right? In other words, the first derivative of the velocity is 0. And what is the derivative of the velocity? It's the acceleration, right? So in other words, it's a curve of 0 acceleration. So what is the acceleration? It's the second derivative of gamma naught. So this is equivalent to say gamma naught prime is identically 0 and gamma naught A is x, gamma naught B is y, right? Okay. So this we know, right? Now suppose we have M is a submanifold of Rn with the induced metric, the induced Riemannian metric. So, okay, before that, let me just, now let me look at a Riemannian manifold first. So in Mg, Riemannian manifold, what happens to the corresponding problem? of finding shortest length curves. So notice here that the first condition, that the length of gamma is the shortest length curve, this is a condition on integrals, right? So this is some integral condition. This surprisingly is equivalent to a differential condition, right? That the second derivative is identically 0, right? So some integral condition is equivalent to a differential condition. And what we will see during this course is that the same happens for a Riemannian manifold. So first of all, I need to define lengths of curves in a Riemannian manifold. So if P is a point in M and VW are tangent vectors at P, then we define the inner product between VW to be GP of VW, since GP is an inner product. And you define the length of the vector V to be GP of VV to the half. Okay. So we can define inner products between tangent vectors at the same point, and we can define the length of any tangent vector. So now that we've done this, if gamma is a C1 curve, sorry, in taking values in M, then we can define the length of gamma to be the integral from A to B of the norm of gamma prime t dt. So the same formula as in Rn, only now the norm gamma prime t is computed using the Riemannian metric G. Okay. All right. So again, we can try and ask, what is, do we have existence of shortest length curves between 2 points? And if so, can they be characterized by some differential equation, as in the case of Rn? So to motivate what's going to come later, let me look at the case now where M is a submanifold of Rn with the induced Riemannian metric. Okay. So, so for example, you have S2 inside R3, for example. And you want to find the shortest length curve from X to Y, 2 points in S2. So how will you do this? Okay. So suppose, let's, to motivate things, let's do a little heuristic calculation. Okay. So suppose gamma is a shortest length curve. Okay, so well, okay, actually, before doing this, let me just let me move this down. There's one thing which I will need first. So let me move this down a bit. No, this is not what I want. Sorry. Hmm. Right, that's right, Bappa. Norm of gamma prime t is g sub gamma t of gamma prime t to the half. Correct. That's right. I mean, I've defined norm v for any tangent vector v, right? So it's g sub p where v belongs to TPM of vv to the half. Okay. I've forgotten how to select and okay, I think I should be able to do it now. Yeah. Yeah, right. Okay. So 1 second. Let me just do it from here. Okay. Right. So there's one thing I want to say first. So we can define the speed of gamma as the function sigma of t, which is the norm of gamma prime t. Okay. And now you've probably seen that in Rn, you can reparameterize a curve so that it becomes unit speed, right? So the same, you can do the same thing in a Riemannian manifold. You can always reparameterize the curve so that it becomes unit speed. So what I mean is, so the length of gamma is equal to sigma of b. Right. So if I look at the interval AB, then this maps under gamma to m, and the length function, the speed function, sigma, sorry, okay, right, that's not what I meant to do. Sorry. Okay, let me call the speed s, and let me call sigma to be, sigma of t is the integral of the speed. So the length up to time t. So the integral from 0 to t, s of u du.
Sir,
Yeah, so let's wait and we'll start again after the meeting ends. Sorry, any question?
sir, will it be A to T?
Sorry, from A to T. Yeah, sorry. Thanks. A to T. A to T. Okay, let's just wait till this ends. We'll join after it ends.